Okay, so today we're going to be analyzing functions using our derivatives. We're going to be going over the increase, decrease of a function, and also concavity. So we're going to find, this has 5 parts. We're going to find part A, the intervals on which the function is increasing, B, the intervals on which the function is decreasing, and then C and D are determined where it's concave up, concave down, and then E we're going to list the inflection points. Alright, so let's get started. So first we'll do part A and B. They're both kind of hand in hand. And so in order to find if the function is increasing or decreasing, well, we could just take the derivative. And if we take the derivative, we know if the slope is positive, then it's increasing, and if it's a negative slope or a negative derivative, then the function is decreasing. So let's go ahead and take our first derivative here. F prime of x is going to be equal to derivative 5 is 0, derivative of 12x is 12. And then derivative of negative x cubed is going to be negative 3x squared. That's our derivative. And so now we're going to find the critical points. The problem's not asking us to find critical points, but in order to find out if the function is increasing or decreasing, you need to find the critical points. And so to find the critical points, you set it equal to 0. And so all it means by critical points is points where the function changes its direction. So if the function is increasing, at some point it'll stop increasing and then decrease. The point where the slope is 0 is where it's not increasing or decreasing. So that's why we set this equal to 0. Then we solve for x here. 3x squared equals 12. We added 3 to the other side, divide the whole thing by 3. We have x squared equals 4. And so x equals 2. X also equals negative 2. Okay, so these are our two critical points. And so we can set up a number line. And here put, this is x equals negative 2. This is x equals 2. And so we want to find the intervals on which it's increasing and decreasing. And then we have 3 different intervals. And so all we do is we plug in numbers less than negative 2 to find out if it's increasing or decreasing on this interval. And then we plug in something between negative 2 and 2 to find out if it's increasing or decreasing on this interval, and the same for greater than 2. So let's try 0. 0 is really easy. So if you plug in 0 for x, you get 12 minus 0. 0. 12 minus 0 is 12, sorry. Which means that we're increasing on this interval. So positive. Positive. Now let's plug in something else. 3, let's say. So 3 squared, 9. 9 times negative 3 is 27. So you have 12 minus 27. It doesn't matter exactly what the number is. All we know is that it's going to be negative. So that means that on values of x that are larger than 2, we're decreasing. Now we'll plug in negative 3, for example. So just something that's smaller than negative 2. Negative 3 squared is 9. 9 times negative 3, 27. You have the same thing. 12 minus 27. It's a negative number. Doesn't matter exactly what the number is. All we need to know is that it's negative. So it's decreasing here. So this can help us answer parts A and B. We can say that f is increasing on the intervals of negative 2 to 2, and f is decreasing on the intervals of negative infinity to negative 2 and 2 to positive infinity. So we'll write that down. Let's erase this and do it in black. F is increasing on, and we'll do the intervals negative 2 to 2. Now we use parentheses, not square brackets, because these values are not included. The function is not increasing at x equals 2. The function is 0 at negative 2, so it can't be included, so it's parentheses. 2 to 2. Now we'll plug in and then f is decreasing on negative infinity to 2 and also to the positive infinity. Okay, so that's A, B. Now for part C, we need to determine concavity. We can determine concavity with a second derivative. So all we need to do is take another derivative of f of x. Or, yeah, f of x. So now we have f double prime. Derivative of 12 is 0. Derivative of negative 3x squared is going to be negative 6x. And in order to find concavity, you need to find the inflection points first. So the way this question is worded is kind of, it's not a very good way to word it, because part E is to list the inflection points, but realistically you need to find the inflection points first before you can determine concavity. Inflection point basically means when you switch concavity, so it's very similar to critical points in that sense. You just set the second derivative equal to 0. And when is this statement true? When x equals 0. So let me highlight this. That's A, that's B, that's E. But we still need to see a D. And so since we know that, this is our inflection point. Now we can draw a number line. I'm going to just do this here. This barrier represents second derivative here. And so the inflection point is x equals 0. And so we're concave up when the second derivative is positive. We're concave down when the second derivative is negative. Pretty straightforward there. So now we need to test numbers less than 0. Any negative number, negative 1 times negative 6, is going to be positive 6, which is a positive number, which means that we are concave up. And then if we plug in a positive number, something bigger than 0, 1, for example, we'll get negative 6 times 1, that's a negative 6. So since it's negative, we know it's concave down. So f is concave up on the intervals negative infinity to 0. 0 is not included again because it doesn't have concavity at that point. It's switching concavity at 0. And f is concave down on 0, positive infinity. This is your answer for part C, and this is for part D.